So I was trying that the first week is rather intuitive, and so we intuitively arrive at the concepts of the metric and the concepts of what are we looking for, how to formulate the classical field theory for gravity. So now this week, the start of the week, we'll still be doing the differential geometry, but then I hope to actually start discussing general relativity, arrive at the Einstein equations, and even perhaps find some simple solutions of these equations. So that's the plan for this week, and then the last week we should discuss some applications. So anyway, so last time we discussed tensors, and basically you should be thinking about tensors as objects which do not depend on coordinates. So in any coordinate system, so whatever the coordinates I use, it doesn't matter because the object remains the same. Of course, this is not true for the components of the object. So this is an example of a tensor. It's a tensor 1, 2. It means that it has one index up and two indices down if you write the corresponding components. And so these are just the numbers. But then it also has the basis, which this is the vector basis and this is the one-form basis. And in between there is a tensor product. And of course it doesn't matter if I write this in prime coordinates, I write primes everywhere. The tensor T on the left-hand side remains the same. But of course what it gives you is that you know how the basis actually transforms under the change of coordinates, and that gives you correspondingly how the components transform. All right. So we also discussed that we need to differentiate these tensors in order to write down the field equations. And so to that purpose, we introduced the covariant derivative. So now let me formalize its properties here. So to be defined in a certain way, and then the following properties would follow. Or you can equally start with this and take it as a definition of what you mean by covariant derivative, and then you can show that that thing will obey whatever we want. So covariant derivative is simply a map which maps K and L tensors to K L plus 1 tensors. It's just simply adding one index down. It must be a derivative, so it is linear and obeys the Leibniz rule. So if you have a product of two tensors, it will act on each of them separately and sum. It has that property that it reduces to partial derivative on scalars. So, okay, so we have seen that this object indeed behaves like a 0, 1 tensor, and it's simple to show that. It commutes with the contraction. So what I mean by that you can equally differentiate this object before doing the contraction. So I have index alpha, and I can differentiate this index and differentiate that index, but it doesn't matter. The result is the same as if I first contract it and then the covariant derivative. Finally, if you take a commutator of the covariant derivatives and act on a function, well, in general relativity you get 0, but more generally you would get the torsion term. And so we define the torsion as simply the antisymmetric part of the connection. So this is the definition of the torsion, and the torsion would actually appear on the right-hand side for this commutator of derivatives. Okay, so now specifically this is how so these are the properties of the covariant derivative, but that's not how we introduced it. I told you, well, for a vector, we can simply upgrade our partial derivative to add the connection term, and so adding this thing here, and so requiring that this object actually transforms as 1, 1 tensor. So that nabla V is a 1, 1 tensor. Okay, and so you know how the partial derivative of a vector transforms, and so you need to prescribe how this coefficient gamma has to transform, and this is the rule. So if your gamma transforms in this way, then this object will be a 1, 1 tensor. So now, of course, the transformation consists of two terms. So first term looks like the tensorial transformation. So this would be the transformation for a rank 1, 2 tensor. However, you have also this part here, which is quite ugly, and so it's precisely this thing compensates for tensorial transformation of the first term. Okay, but notice that if you are in special relativity, these two derivatives and in Cartesian coordinates, well, in Minkowski coordinates, then this term would cancel, and so in special relativity, this object gamma is a tensor, but not in general relativity, not for general coordinate transformation. Okay. So now we know how to do for a vector, but we can also infer from this how to do a covariant transformation of a one form simply using the properties here. So now the statement is that the commutation is contraction simply gives me that tabla alpha omega beta, so this is how the covariant derivative acts on a form, is equal to d alpha omega beta minus gamma gamma beta alpha omega gamma. So that's how a one form would be differentiated. Well, and then to see this, I'll just do it very vaguely. So the idea is that I know how this guy transforms, how to act with the derivative on this guy, and I know how to act with the derivative on a scalar. So in order to get a derivative of a covector, I simply consider a covariant derivative. So proof of this would be that I act with a covariant derivative on a contraction of vector and a form. Okay. So then this is just a scalar. So what I mean is V alpha omega alpha here. So this is just a scalar. So I know that this simply is a partial derivative. Okay. So I'm using the property number 2. But I can also use the Leibniz rule. So this will be equal to nabla v times omega plus v times nabla omega. So that's property number 1. So I'm using the Leibniz rule. But let me just check that this whatever here is correct. Okay, so nabla v very schematically is simply partial v plus gamma times v times omega, and then I just want to verify that this thing is true. So in that case, this is equal to nabla omega is just d omega minus gamma times omega. Okay, very schematically. Of course, there are some indices and there are some contractions there, but who cares? So now see, this term is that term plus this term is that term is simply a partial v dot omega. So that's the terms which do not contain gammas. But then I have plus gamma v dot omega minus gamma v dot omega, and hopefully that the contractions, when performed correctly, actually give you 0. So this cancels that, and this is what I need to have. So this works. Okay, so this is how you would derive that this thing is the transformation property. Of course, if I don't know this, I can calculate it directly from here. I know this guy, and then I just read off what that guy is from that equality. Okay. So then for a general tensor, of course, it's just it acts on each index separately. So general tensor. The covariant derivative, nabla alpha, d beta, and then I have some indices up as well, is simply d alpha, d beta, gamma, and then for indices which are up, I have a plus gamma term. So it's gamma delta alpha, d beta, delta, and so on. And then for indices which are downstairs, I have a minus gamma term. It's minus gamma rho, beta alpha, t rho, gamma, and so on. So this is how you would differentiate a general tensor. And of course, once you know how to differentiate a vector, once you know how to differentiate a form, you just treat tensor as a product of forms and vectors and use the Leibniz rule, and then you can derive this general formula here. So of course, this gives you a general prescription. So if you require that you have a derivative which is linear, satisfies Leibniz rule, and so on, it's typically to show. It's typically enough to show some properties of this derivative just for a function and let's say a vector, and then everything else follows because I can use the Leibniz rule for any other object. Okay, so if you are proving some identities valid for derivatives, for Lie derivative you will be proving some identity in the gravitational physics course and so on. It's enough to show it for scalar and for a vector, and then everything else follows. All right, questions to covariant derivative? Okay, no questions. So, and part D, metric. So far, everything we have done does not depend on the metric, and so the metric was not needed anywhere in our considerations. So you can happily differentiate tensors without having a metric. But if you have a metric, the life gets simpler, and actually there is a preferred connection, which is much nicer than this general thing here. So what is a metric? So metric, the middle one, metric G is simply a symmetric 0 to tensor field on M. Okay. So if you want the corresponding matrix G mu nu is symmetric, and what we will also be requiring for general relativity is that this metric is pseudo-Riemannian. So pseudo-Riemannian in GR. That means that it actually has 3 positive and 1 negative eigenvalue. So the metric would be Riemannian if it had only plus eigenvalues, but we live in this strange signature case where you have 1 minus eigenvalue, so pseudo-Riemannian. So, of course, it's a metric, so you should be writing it, it's a 0 to tensor, so you should be writing it simply as dx mu dx nu, and you should remember that it is symmetric here. So now people typically don't write the tensor product, and they would just write it just g mu nu dx mu dx nu. So this is what you should be writing. It's simply an invariant tensor, which is given by its components and the corresponding basis. But then people also write something crazy, and they just write this is equal to ds squared. Okay, this of course doesn't make any sense whatsoever, because you know that whatever stands on the left-hand side is a tensor, and this is the basis. Okay, so this is the basis, and these are the components, and simply this is an invariant object. So this is a misuse of language, which is only actually happens for the metric. People don't use it for any other tensor, only for the metric. And the reason is, of course, the metric is a 0, 2 rank tensor, and so it likes to eat vectors, right? And so if it eats 2 vectors, v and w, it produces a number. So that's how these 0, 2 tensors. So this is, and the number, of course, what it is, it's just g mu nu, v mu, w nu. It's a scalar product of the 2 vectors, so this is a number. So now how you interpret that number is that basically you say, well, it's a scalar product of these 2 vectors. In particular, if I plug in v equal to w, it will tell me how big the vector v is. So specifically v equals to w. So this tells me like a scalar product between two vectors. But if I take v equal to w, then g v will tell me how big v is. It tells me the magnitude of the vector v. Right? So now, when you want to interpret this as some number ds square, as an invariant metric element, what you really mean is, well, let's interpret this dx mu as some vector. So which tells me I'm moving, in the space-time along the vector dx mu. And I'm feeding it to the metric. So this interpretation here is really chi dx mu dx nu, where these things are treated as vectors. And so then, this is the same, well, whatever. And then it tells me, how big these vectors are. So this tells me, how to measure distances in the space-time. So that's this interpretation of ds squared. So how big is this infinitesimal distance if I move dx mu in the space-time, where dx mu is now treated as a vector. Okay? Well, this is a really, really crazy thing, and I would prefer people did write only this, right? So this makes sense. It's a tensor. There's some component, some basis. But, historically, people also say, well, the metric actually measures the distances in the space-time, and then they have this misuse of the language that dx mu suddenly are treated as vectors, and it just tells me how big these vectors are in the space-time. All right, so that's what a metric is. So now I said that in the presence of the metric, we can define a preferred connection. So another thing will be Christoffel symbols. Are there any questions to this? Oh, everything is clear. Everything is clear, right? So what Christoffel symbols are? So you may have a great idea that you have the covariant derivative and you have the metric, and then you simply form a tensor out of that. So let's form a tensor m alpha beta gamma to be nabla alpha g beta gamma. And this tensor is called metricity. Okay, well, it's a covariant derivative acting on 0, 2 tensor, gives me 0, 3 tensor, and it's a metricity. Then I have this another tensor, which is the torsion tensor. So I have the torsion as well. So T alpha beta gamma equals to gamma alpha gamma beta minus gamma alpha beta gamma, which is the torsion. That's another tensor. And then the theorem, which is actually very easy to show, but I will not do it because it's just annoying. So theorem says, so at this point, these gammas are just any general connection here. So all I require is that they transform in that way. So theorem is provided that the metricity is 0, so m alpha beta gamma equals to 0, and the torsion is 0. P alpha beta gamma is 0. Then there exists there exists a unique connection given by Christopher symbols. And this connection is simply given as you know it, as we derive it, I don't know, the second lecture from a simple way. And it's given by gamma alpha beta gamma equals to 1/2 G alpha delta, and then G. So again, it has to be symmetric in beta and gamma. So it's G beta delta gamma plus G gamma delta beta partial derivative minus G beta gamma delta. Okay, and that's the theorem. So if there is no torsion, and if there is no metricity, the metricity vanishes, then the connection is actually given by, in terms of the metric. So in other words, the metric now is the only independent object in the space-time. So before, in order to write down the covariant derivatives, we had to have these objects, gammas, living in the space-time. So now we can get rid of these gammas. These are entirely given in terms of the metric, provided these two conditions are true. All right? So by the way, it's very interesting. So this is general relativity. So general relativity assumes that there is no metricity and then there is no torsion. It's very simple to include generalizations where the torsion is non-zero. And it will be true for any supergravities or for string theory, low energy limits of the string theory. They will have torsion. And typically this torsion is associated with some fluxes of something like Maxwell fields, but higher rank Maxwell fields. It's much more complicated to construct a reasonable theory where you have metricity. And actually, I thought there is none. But I went to a conference this spring, and so actually a person who is somehow associated with PI told me, yeah, we have a theory where actually you have also non-trivial metricity, and this metricity is dynamically determined. So typically, you have torsion whenever you have spin. So if you have matter with lots of spin, then you have non-trivial torsion. So now they came up with the theory where you actually have some source for the metricity as well. Okay, so I can give you a reference if you're interested. Anyway, so this is general relativity.
David?
Yes.
I'm sorry. Why did the Christoffel symbols appear like 2 lessons ago? Why were they there? I mean, why did they naturally appear from what we were doing?
Okay.
Before?
Well, what we were doing is that remember. So for example, if you look at the torsion is just the antisymmetric, where you antisymmetrize the lower two indices in gamma. So now when we were, for example, doing this very intuitive way to general relativity, we basically define this we define this connection by going from flat space to some curved coordinates, right? And in our definition, this connection was automatically symmetric in these lower indices because it was just a transformation of something. And it came out to be, some partial derivatives. So we, for example, immediately kill the torsion.
Okay, great.
But anyway, so this is the thing which matters for general relativity. So it was correct what we have done. All right. So now we want the statement is the equivalence principle. So let's put So if you're interested in the proof of the theorem, it's actually in the lecture notes, but it's not that illuminating. You just use both conditions, and this is what comes out. Okay? So the equivalence principle, and let's formulate it in increasing generality. So one formulation is that at a point, I can always set G mu nu equals to eta mu nu. So I can always make the metric look like a Minkowski metric? Well, if you formulate it this way, it's a trivial statement. Why is it trivial? So at a point, I look at my components of the metric G mu nu, and the metric is symmetric, so it's a symmetric matrix. And so you know that there is a diagonalization process called Gram-Schmidt diagonalization process, and it tells me that I can always find such rotation of coordinates, whatever, so that so that I have only diagonal piece, and on the diagonal I have the eigenvalues of the matrix, right? So this is through Gram-Schmidt diagonalization at a point. Gram-Schmidt diagonalization. And of course, if I have some eigenvalues on the diagonal, one of them has to be negative and 3 have to be positive. But I can always actually decompose these eigenvalues to something which is -1, 1, 1, 1 times something else. Okay, so basically the statement is very simple. So I have G mu nu, dx mu, dx nu. That's my metric. And so let's write it pretending that we are doing the matrices. So I have a vector of dx, and then this is my metric matrix, and then I have dxt. And so the Gram-Schmidt tells you I can always write this G as some orthogonal matrix, diagonal matrix, times another orthogonal matrix. Okay, and where this D simply has minus lambda 0, lambda 1, lambda 2, lambda 3 on the diagonal, and 0 everywhere else. So here I've chosen all these eigenvalues to be positive, and I'm writing this explicitly, the minus sign corresponding to the negative eigenvalue, which of course I can also write as minus E0 square, E1 square, E2 square, E3 square, because they are simply all positive. All right, and so then introducing a new matrix, L, to be the square root of this matrix. So it will be E0, E1, E2, E3, and 0, and 0. You can write the diagonal as the Minkowski metric times L times L. Okay, so if I continue writing this, I can write it as D, XT, OT, but now I write the diagonal as LT, my Minkowski metric, L, O, and dx. So this is what the diagonal was. Now I'm taking the square root of that. I'm preserving -1, and then if you multiply by L, this is what it is. Okay, but now the last step is to simply call this thing my new coordinate, dy, and then surprise, surprise, this is my new coordinate, dy transpose. And so you just manipulated the thing into dyt eta dy. And so you see that in these new coordinates y, my metric looks like eta metric, like the Minkowski metric. Okay, so this is just a linear algebra, right? We are not doing anything fundamental here. At a point where everything is, fixed, the coordinates are fixed at the point, I'm just diagonalizing the metric, and that's just a linear algebra. Yes?
Where did we assume that it has to be at a point?
Oh, well, this Gram-Schmidt. So at a point, whatever the components of the metric are, they will, in general, these things, they depend on the coordinates, but at a point you have some values of these coordinates, right? If you start, moving outside of the point, these things are really functions, and once you are outside of the function, well, it's not that simple, right? So you would have to be doing the diagonalization procedure in this point differently than in that point and whatever, right? So this diagonalization, this thing here, really you can do it only at a point, because if you do it in another point, it will be different.
So we're actually doing it on numbers, right?
Is there like a theorem which guarantees that if G mu nu changes a little bit or continuously, so will the new basis vectors?
Well, I guess it must be so, because we can also set derivatives to 0. Yeah, so I think so. Yeah. All right, so this is the simplest way of equivalence principle. So now, a more sophisticated way, actually we can do better than this, is the following formulation. So at every space-time point, it is possible to choose a coordinate system, to choose coordinates of course we call this a freely falling system, freely falling or inertial coordinates so that in the nearby neighborhood we have the special relativistic laws. We have special relativistic laws and our metric looks like the flat metric eta mu nu, G mu nu equals to eta mu nu. But also we can do more. We can actually set all the derivatives of the metric equal to 0 at a point. Okay, so this is basically the equivalence principle as we discussed it before, but now it's a little bit more formalized. But you see that not only the metric can be set to the flat metric, but also the derivatives can be set to 0. And if the derivatives are set to 0, if you look at the formula above, it means that the Christoffel symbols are 0. Okay, so this means also that gammas are equal to 0. So basically you can get rid of gravity locally, but if you remember, the gammas actually tells you about the geodesic equations, and so there was this piece which was like d square x mu over d tau square plus the gamma part. So now we are setting gamma part equal to 0, so we are back in the flat space, and so we have straight lines in this freely falling system. Okay, that's how we started discussing the geodesic equation. That we said we have the freely falling system, and then just look at it how it looks in curved coordinates, and then the gammas appeared. But this is precise. Now we are going backwards, right? Now we are saying we have in general gammas, but we can get rid of them at least, it's some close by neighborhood.
How can you take a derivative at a point?
Well, you are taking a derivative and evaluating that at a point. So you first take a derivative and then you evaluate it at a point. All right. So now to prove the second is slightly more complicated. So we already shown that we can set G mu nu equal to eta mu nu by this diagonalization process. But when you are talking about the derivatives, precisely you have to take the derivative first, and then you evaluate that in that point. And so you need to do a little bit more work. So what I will already show you how to prove this is a counting argument. I will not show you that it can really be done. Well, sort of. Okay, so proof. Not really. rather just a counting argument. All right. So what we want to do is that we have some general coordinates where my metric is curved and where my derivatives are non-zero. So now we want to change the coordinates so that in those coordinates at that point this is true. Okay. So seek a coordinate transformation. So let's say from x to x prime, so that in my new x prime coordinates, that thing will be true. Okay, so without loss of generality, I can place the point P in the origin of both coordinate systems at x and x prime. So then you may proceed order by order in the expansion in OX. So in the first step, you say that my x prime alpha, the coordinate, is simply linear in my old coordinate x plus OX squared. Right? So I'm placing the origin at the same, the point P is in the origin of both coordinate systems. That's why I don't have the absolute term. So the first term is the linear term. I'm doing the Taylor expansion in x. Okay? So then, if you are interested how the metric looks like in these new coordinates, you just do a coordinate transformation on the metric. So G alpha beta prime, and then you evaluate it at the point P, is simply, now it's dx over the, it's dx prime over the x, and dx prime over the x, and then the old one. So now dx prime over the x is simply this matrix A alpha beta. Okay, so this is x prime dx alpha gamma dx prime delta dx beta g gamma delta. Okay, so that's equal to A alpha A gamma alpha A delta beta and then G gamma delta at the point P. Okay, so this is how my metric looks in these new coordinates, and what I want is that it is a flat metric. So what you want is that this is equal to eta alpha beta. That's what we want. So now you see, so in order to prescribe these new coordinates, I'm inventing this matrix A alpha beta so that this is the relation, so that this thing is true. Okay? So in other words, I'm solving this equation for A's. Okay? However, this equation, how many equations do we have? How many equations is this equation? Huh? This, does it have any symmetries? Well, okay. Yeah, very good. It's diagonal, but it's symmetric. Okay, so that's right. So we have actually, 10 equations. 10 equations. And we are solving these 10 equations for my unknowns, which are A's, for, and how many are these? 16. For 16 unknowns, A alpha beta. Okay, okay. So if you are lucky, you can always solve this equation, right? So I can always find such A alpha beta so that I can satisfy these things. So I can always do it. In fact, actually, you have a freedom of specifying 6 components A alpha beta. Okay, what is this freedom? Anybody see? Huh? Exactly. So you remember that, you know, this thing is left invariant by the Lorentz transformations, right? The Lorentz transformations precisely have 3 rotations and 3 boosts. And so the remaining 6 correspond to Lorentz transformations, which leave my equation unchanged, Lorentz transformations. So, you know, by just counting argument, you see that you can always set eta alpha beta equal to 0. In fact, we did it explicitly over there. Okay. So now let's look at the derivatives of the metric. So to that purpose, we already fixed our A alpha beta, but now we go to a higher order in X. So next, we consider X alpha to be A alpha beta X beta plus 1/2 B alpha beta gamma X beta X gamma plus OX cube. So these are already fixed. So that we have G alpha beta equals to eta alpha beta. And so these are my new coefficients, which I can, you know, choose arbitrarily so that my derivatives of the metric vanish. So now, if you look at this expansion here, this object is X beta X gamma, and it's symmetric in beta and gamma. So in other words, this thing also has to be symmetric in beta and gamma, because if it is not, it doesn't matter. If it's antisymmetric, it doesn't contribute to the problem. So we have these B alpha beta gamma when it's symmetric here. So how many of these objects I have at my disposal? So I have 10 of those because they are symmetric, and then times 4, so it's 40 objects. Now, what I want to do, I want G alpha beta gamma equals to 0. How many equations are these? So the metric is symmetric again, it's 10, and times 4, so it's 40 equations. So if you are lucky, you can use these 40 objects, B alpha beta gamma, to actually, you know, make these derivatives to vanish. You have 40 objects to do it, and you have 40 equations to impose. Okay, so this can be done, and you can, by going to the second order, you can actually set the derivatives equal to 0. Okay, so let's see how far we can go. So next, so the question is, can we set G alpha beta gamma delta equal to 0? Okay, so can we also at a point eliminate the second derivatives of the metric? How many equations are here? Huh?
160.
160.
Say 100.
So this guy is symmetric, right? So it's 10. What about this guy? So 100. So 100 equations. All right. So now if I keep going here, so now I add my 3 terms. So that will be 1 over 3 or whatever. B alpha, well, C alpha beta gamma delta X beta X gamma X delta plus OX4. Okay, this object is symmetric in beta, gamma, and delta. So this object must be symmetric in beta, gamma, and delta. Okay, So how many of these objects?
16.
Okay, so just draw this, and you will find out what it means. 4, 5, 6. So we are choosing the indices take 4 values, right? So that's why you start in 4. And then you have 3 indices, and they are symmetric. That's why you go 4, plus 1, plus 1. 4, 5, 6. This is a Young tableau, which calculates how many symmetric objects are there. Okay, and so the prescription what this picture means is 4 times 5 times 6 divided by 1 times 2 times 3. Find about Young tableaus in the Wikipedia. So anyway, so this number, it calculates how many are these here. And if you find it, it's actually 20. So the statement is that an object which has 3 indices, which is completely symmetric in these 3 indices, and each index takes up to 4 values, has 20 components. However, I have also this index alpha here. So it's 20 times 4. Okay, so C alpha beta, gamma, delta has 20 times 4, which is 80 components. Okay. So we have, if you want to set second derivatives of the metric equal to 0, we need to solve 100 equations. However, by going to the third order, it gives us only 80 components to fix. Okay, only 80 components of C we can do. And so there's a discrepancy of 20, and I cannot set these derivatives equals. So we missed 20 components. And that means that you can set almost all second derivatives of the metric equal to 0 apart from 20. Of course, this is just a counting argument. I'm not really doing this explicitly, right? So we miss 20 components, and that's why there will be the 22nd order derivatives of the metric. Left. That means I can get rid of almost all second derivatives but 20. Okay? So now you'll see we can combine these 20 into a nice object, and that object is called Riemann tensor. Okay? These can be combined. To the Riemann tensor. And so what it's actually telling you that the Riemann tensor will have 20 non-trivial components. So now Riemann tensor is a 1-3 tensor. So it's a 1-3 tensor. So it has components are alpha, beta, gamma, delta. So now you see that again, if I calculate how many such a beast can have components independent, well, this guy is 4, 4, 4, 4. So 4 to the 4 components. So you see that in order actually this statement be true that it only has 20 components, there must be huge symmetry to this tensor, and we will see it in a minute. So a lot of symmetry. is hiding in this Riemann tensor so that only 20 components are independent. All right, so we have seen that now, by doing this counting argument and doing the coordinate transformation, we can we can make the metric to be flat. We can kill the first derivatives of the metric, and we can kill almost all second derivatives apart from 20, and these will be encoded in this Riemann tensor. So now, even more general equivalence principle. And so everything that we are doing here was at a point. Okay, so at that one point, we could set the derivatives equal to 0. But the truth is that you can do it not only at a point, but you can do it along a trajectory. So let me discuss a geodesic. So let gamma be a geodesic. Then the statement is, along this geodesic, along the whole geodesic, you can actually choose the coordinate system such that you will see that the coordinates look nice, but it means that along the whole geodesic, g mu nu equals to eta mu nu, and gammas vanish. Okay, and so the coordinates, how you choose them, is that you have some time coordinate t, and then you have some space coordinate, and there will be xi. And so simply the coordinate system where the metric vanishes and the metric is flat and the gammas vanish is such that t is simply the proper time along the geodesic. So this is my t again. So t is the proper time along the geodesic. So that's my coordinate. And then the xi are simply the coordinates which I drag with me, xi, but they are such that the geodesic is at 0 all the time. So all the xi is equal to 0 is where my geodesic is. And so these are the special coordinates which I drag with for my observer along the geodesic. And then you can show that in these coordinates, so in coordinates t and xi, so again, t is the proper time along the geodesic, and xi are such that xi are 0 on the geodesic. The metric can be written as gtt equals to -1, and then the linear term vanishes, as we discussed over there, and then you have the quadratic term, ti, tj, xi, xj, plus ox cubed. So this is the absolute term. The metric is equal to -1, gtt equals to -1, as in flat case. Then the linear term is gone, and then you have quadratic term, and of course this is just the components of the Riemann tensor of that object there. Okay, and that's gtt, and then you have gti. Of course, if this has to be flat metric, the absolute term is 0 minus 2/3 or t j I k xj xk plus ox cubed, and then gij is delta ij minus 1/3 ri mj n xn plus ox cubed. Okay, so you see that the metric is flat metric. The first derivative of the metric on the geodesic, where x is equal to 0, will be 0, because it's just one derivative with respect to x, but there is no linear terms here. So that's why gammas are 0 along the geodesic. And so the only thing which contributes at the quadratic order is precisely this Riemann tensor, which contains the information about the two derivatives. Yes?
Why do we have a 2/3 and a 1/3?
Oh, it just comes from the calculation. Yeah. So you see, so this is some specific object, And these things they just come some combinatorial apart. Yeah.
And this analysis is totally dependent that we are in 4 dimensions, right? We're assuming that we are this counting of the how many.
Yeah, you can do the same counting in higher dimensions, and you'll find that in any number of dimensions you can always get rid of gamas. But of course, the Riemann tensor has 20 components only in 4 dimensions.
What about 3 dimensions?
Oh, very good. Wait, you will do the whole tutorial on this. So you will be counting more than you want. You'll be counting. You will be discussing general relativity in all possible dimensions. And I think it's Friday's tutorial. So wait for that, please. It's a good question. Yeah.
One question is, so when we are, for example, fixing A's in this argument, we fix the metric, then we include B's.
Yeah.
How do we know that these B's will not change the first argument that we tried to fix?
Oh, because so you are always so here the point is such that I'm choosing x equal to 0, right? So at that point, so that's that I said that the point is such that my coordinate system coincide and they have x equal to 0. So now if I differentiate this thing once, then in the end I have to plug x equal to 0, right? And so this time will actually not affect whatever the metric looks like. Something like that. All right. So now this is the first encounter of the Riemann tensor. And as I was saying, so the most general equivalence principle is that you can actually choose freely falling system along the whole trajectory, not just at a point, but along the whole trajectory here. By the way, these coordinates are called Fermi coordinates because Fermi was the guy who studied it and used it. So Fermi. And of course, he was one of the physicists who actually knew the answer before he calculated anything. So he's famous for his back of the envelope calculations, like always doing like 3 lines and knowing the answer. So of course, when there was this first test of atomic bomb, they wouldn't let him, close by because he was Italian, right? And so maybe it was an alienic force or whatever. A spy hiding somewhere, so they wouldn't let him, go nearby. But anyway, so he was like 50 kilometers away, or maybe even more, and he just looked at the explosion, and then in 3 lines he estimated the power of the explosion. And then when they talked to him, I said, "Well, the explosion was of this power," and they just couldn't believe that that he's not a spy because he just could estimate it from something. So anyway, so Fermi, very very interesting person. All right. So we have the equivalence principle. Now, what we will be doing is that we will discuss general relativity from the variational point of view. So we will write down the action, and then we will vary this action and derive the corresponding equations of motion. And for this, you need to know how to integrate things. So how to write down the invariant volume. So next thing is the invariant volume element. Is there a question? No. Okay. So what I'll be doing is that I will be writing G, which will be a shortcut for determinant of my metric G mu nu, because the metric has this weird signature minus plus plus plus. The determinant comes out to be negative, so this is smaller than 0. And so if I want to take square root of these things, I'll always be taking square root of minus G, so that it is positive number. So anyway, so we have the transformation law. Which is probably wrong there. So G mu nu prime is dx alpha, dx beta. It's probably wrong there. Dx prime mu doesn't matter. Dx prime nu G alpha beta. So that's my transformation law, which doesn't agree with that one. Sorry for that. Hopefully this is correct. So that's how I transform. So now I look at this thing here, and you may think about this thing as a matrix with index alpha and mu, and this thing as a matrix beta nu, and this thing as a matrix alpha and beta. So if you want to take the determinant of these things, so here I'll have G prime, taking the determinant of that. But then if I have product of three matrices, then the determinant is simply a product of determinants. So it will be determinant of this dx over dx prime times determinant of dx over dx prime and times g. However, this is just a Jacobian, so you can write it as dx over dx prime square g, or if I want the inverse transformation, it's a dx prime over dx to minus 2 times power g. Okay, so now if you look at this thing here, so I have G prime, so G prime equals to Jacobian of the transformation dx prime over dx minus 2 times the original determinant. This is certainly not how a scalar should transform. So you know that the scalar simply transforms that phi prime equals to phi, but now in here we have this thing in addition to that. Okay, so this is, it looks like a scalar, but determinant of the metric is not a scalar. So determinant of the metric is a scalar density. Scalar density. And then of weight plus 2, because there is a minus 2 here. So you always weight the scalar densities in terms of negative powers. So now I have negative plus 2, and so that's why it's of weight plus 2, scalar density of plus 2. All right, so the determinant does not transform as a scalar, but it still has relatively nice transformation. So now let's look at how the volume transforms. So now if you take dv prime, which is, let's say we are in n dimensions, x prime. So now if you want, so this is in my new coordinate system, so I have n-dimensional measure or n-dimensional volume thing in x prime. So if you want to write it in terms of x, you pick up the Jacobian of the transformation. Again, so this is dx prime over dx times dnx. So with changing coordinates, the volume changes with the Jacobian. So this is dx prime over dx, and then dv. So this is not also not a scalar, right? So the dv thing is also a scalar density, but now if I want to write with minus, so it's of weight minus 1. Okay, so scalar density of weight minus 1 now. However, so I have two problems. So the volume is not a scalar and determinant is not a scalar, but maybe the two problems actually combine together to solve everything. And so if you combine the determinant with the volume, you get something which is a scalar and which is nice. So then the statement is that you can define an invariant volume element invariant volume element. So in other words, well, this sounds great, but what it means is a scalar. And so let's write it as dv to be minus g and then dnx. And this will be invariant because this thing, now if I take a square root of that, it has a weight +1. This has the weight -1. In the end, they combine together to give you a scalar. So this is a scalar. So when you will be writing the action, of course, well, composes of the Lagrangian density, and you have to integrate that over the space-time. So then, if you define the Lagrangian density to be a scalar, then you have to integrate it this way here, so that the result is a scalar. The action is a scalar. Questions? So this is all nice. So the one thing which we will not really need, but well, for some things it's useful. The point is that when we discuss special relativity, we had this Levi-Civita pseudo tensor, which was defined to be, well, it was an epsilon, and if the indices were 1, 0, 1, 2, 3, then you had a +1, and then if it were even permutations, it was still +1. If it were odd permutation, it was -1, and otherwise it was 0. And this was a useful object when you were taking Hodge tool of objects and stuff like that. So now the problem is that in general relativity, this object is not a tensor. It's a tensor density again. So you have to upgrade it with this determinant of the metric as well. So Levi-Civita tensor. And so to define it, you first define this weird object here, rho sigma. You just have brackets and antisymmetrize indices, mu nu rho sigma. And this you define to be +1 if it's 1, 0, 2, 3, and even permutations. And then you have -1 for odd permutations. And then you have 0 otherwise. So it's just +1, -1, or 0. It's just a number. So now if you look at how this thing transforms under coordinate transformation, you will find it's not a tensor. It's a tensor density. Again, there's this Jacobian entering the thing. And so the right thing to define is that once you have this object here, you just say that the tensor, the Levi-Civita tensor, epsilon mu nu rho sigma is equal to square root of -g, and then this symbol here, mu nu rho sigma. And then you can check that this object already transforms as a tensor. So similarly, you can write it with indices up. It should be, these can be raised with the metric, but if you just want to define it in terms of this guy, it will be 1 over square root of -g, but now with a minus sign, mu nu rho sigma. And this is just a thing which you get by raising indices of that one. Okay, so this is, so it's almost like in special relativity. But in special relativity, we have the metric which is eta. It has determinant equal to -1. So this is minus minus 1 is +1. So this is just 1. And so there's no problem there. Yeah?
Why would this object, which is just ±1, transform as a tensor.
Ah, so you want me to prove this?
I don't really see how it would transform.
Okay. Okay, I was worried about that. So I wanted to skip the derivation of this, but okay, let me do it then. Okay, what can we do? So proof. So you take this object and then you look at, so this object has 4 indices, mu, nu, rho, sigma, right? And so now you do like a coordinate transformation if this object were a tensor. So you consider an object, oh no, I have it for alpha, beta, doesn't matter. So if you have alpha, beta, gamma, delta, that's my object. And if you transform it as a tensor, it will have to transform this way, dx beta, dx gamma, dx delta, and then I have alpha prime, dx prime, beta prime, dx prime, gamma prime, dx prime, delta prime. Okay, so this is what we need to study, right? This is how a tensor would transform. So now if you look at what this thing here is that I sum over the indices alpha, beta, gamma, and delta. So the indices which are left are prime indices here. But because I antisymmetrize, this is antisymmetrization, I antisymmetrize over all these alpha, beta, gamma, and delta. I hope the resulting object is antisymmetric in alpha prime, beta prime, gamma prime, delta prime. So it must be proportional to, so let's write it times lambda times alpha prime, beta prime, gamma prime, delta prime. So this must be true. So that it must, so whatever is here is completely antisymmetric in prime indices, which is this thing here, and there must be some proportionality factor here, lambda. Okay, so far so good. So if this is true, then let's find what this lambda is. And the way how you find this lambda is that set alpha prime, beta prime, gamma prime, delta prime equal to 0, 1, 2, 3. If you set it equal to 0, 1, 2, 3, then this thing here, 0, 1, 2, 3, is just plus 1. So then this thing becomes plus 1. And this thing becomes 0, 1, 2, 3. Okay. So now, so this thing will be now 0, 1, 2, and 3. So now if you look at this thing here, what's written here is really a determinant of the matrix dx over dx prime. Right? So if you remember how to calculate a determinant is that you take the product of the completely antisymmetric object times so the prime here, and then this is like how I calculate. I take products of all possible things in the matrix, and so this what is written here is really a determinant. So then this thing here is determinant of dx over dx prime. Okay, and it's equal to lambda times 1, so it's equal to lambda. Okay, so we have this. But if you look at somewhere here, okay, let me just pull it down here. You know that you can write the determinant. So you can write dx prime over dx. So you have g prime over g, square root of that is just dx over dx prime. Right? From that formula here, you have square root of g prime over g is dx over dx prime. And so lambda is simply just given by minus g prime over g. Okay? Very good. So now let me write these indices back. Alpha prime, beta prime, gamma prime, and delta prime. So lambda is just square root of minus g prime over g. So if I redistribute my lambda, I leave the minus square root of minus g prime here, and I put the square root of g on the left-hand side, I will see that the object, okay, so let me just put it here. So I'll write this as square root of g and square root of minus g, square root of minus g, and then you see, and there's a g prime here. So then you have this object here, which is in the prime indices, square root of g and the prime thing. And then you have square root of g and the object without the prime thing. And then you have the transformation rule for a tensor. Okay, so this object really is a tensor and transforms as a rank 4 tensor. That completes the proof. Oh no, that was painful. Okay, but does it make sense? And so that derives that this thing actually is a tensor. Oof. Questions, comments? All right, so now we understand everything about the metric which we need to understand. So let's now discuss something else. We have some time. Let's discuss parallel transport and geodesics. So part E will be parallel transport and geodesics. So again, we already know what the geodesics are because we had this intuitive argument. So let's just do it again. So we consider a curve gamma, which you parameterize by some parameter lambda. And then this curve gamma has the tangent vector with u mu is dx mu over d lambda in some coordinates. So that's the setup. I have u mu here, another mu mu. So u mu is the tangent vector to this curve. Then definition. You define a directional covariant derivative of a vector v along gamma you denote it by capital D, and so let's calculate it for the components of the vector v alpha. So this is what it is. And so how we define it is simply u mu nabla mu v alpha. So you just take a covariant derivative, but make this covariant derivative directional along the curve gamma. So this is like I am projecting the covariant derivative on my direction of my curve u mu. Okay. Sometimes people write it, they actually absorb this u inside here. So they write it nabla u v alpha. And sometimes people just write dot. So the dot means the derivative of v with respect to the parameter lambda here. It's just a shortcut for notation. Okay, but all what it is that, of course, if I replace the covariant derivative with the partial derivative, this would be just a directional derivative of v along u, right? All right, so that's definition number one. Then you say that vector is parallel transported along gamma, parallel transported along gamma when this directional derivative is equal to 0. When nabla u v alpha equals to 0. So vector v will be parallel transported along my curve gamma with the tangent vector u, provided that nabla u v alpha equals to 0. Okay, so now expanding whatever the covariant derivative means in terms of the partial derivative plus the connection term. So this explicitly gives that d v alpha d lambda plus gamma alpha beta gamma u beta v gamma equals to 0. So the vector v is parallel transported along u, provided that this is true. As we will see in a minute, what it means is that actually the vector field u and the vector field v remain the same angle in between them. So no matter how this thing actually I transport this, the angle in between the two remains the same. But of course, what does it mean? This thing here is that you want to make, you want to transport the vector, keeping it constant. So now if you have, if you are in frame, well, if you are in Minkowski space, the gammas are gone, and in Cartesian coordinates, the gammas are gone, and so you really say that the vector is parallel transported if the components of the vector do not change as you move them in the space. So this would be, so in flat case, this simply means that v alpha equals to constant, right? So this thing is gone, Christophers are gone, and these are just constant. So really you are trying to keep the vector constant. And this is just a generalization of space of what it means vector constant. Questions, comments? So finally, a geodesic is a curve along which the tangent vector is parallel transported so nabla u on u alpha equals to 0. Okay, and of course, what it means is that instead of v, I'm just plugging u here, so I'll have d u alpha d lambda, and then beta gamma u beta u gamma, which is the geodesic equation we have seen before, right? So it's fine. Okay. So geodesic equation is really the tangent vector is parallel transported along the curve. So it's such a curve so that the tangent vector is parallel transported. All right, so now just a warning. This nice equation here, W u alpha equals to 0, is, well, will change if you change the parameter lambda. So at this point, I said, well, I just parameterize my curve by any parameter lambda, and so then I require that I have a geodesic so that this is true. So the statement is that if you actually change lambda, in general, and you have a geodesic, but you just change lambda. So changing lambda to some lambda tilde, in general, disobeys this equation. So even if I have a geodesic, which I know that the tangent vector is parallel transported, if I change just the parametrization, results in the following change, then you will have d u alpha over d lambda tilde equals to some function of lambda tilde u alpha. So the statement is, if you find that your curve, that your tangent vector to the curve satisfies this equation, it's still a geodesic equation. It's still geodesic, but in stupid parameter, stupid lambda tilde. So you are using stupid parameter lambda tilde, and the statement is there always exists a parametrization of the curve going back, from lambda tilde to lambda, so that you can get this thing here. Okay. So now, if f equals to 0, the parameter is nice, and that parameter is called affine parameter. So affine parameter simply is a nice parameter which kills this right-hand side to be equal to 0. And you can always find such parameter, lambda tilde. Okay? Are there any questions so far? So let me stop here. Tomorrow we will discuss curvature and start general relativity if time permits. Okay? So see you in the afternoon.